We're going to be looking at word problems that is going to either ask us to minimize a quantity or to maximize a quantity. And more importantly, we're going to have to come up with two equations that's going to relate two variables. The problems I've selected come from page 319 of your book, very similar to the homework problems that I'm asking you to do. So let's read number 3. We have an owner of a ranch that needs 3,000 yards of fencing, or he has 3,000 yards of fencing to enclose a rectangular piece of grazing land along a river. All right, so I've got my river, and I want to come put fence around it, but I don't want to put fence along the river. Fencing is not required along the river. What are the dimensions of the largest area? Well, let's see. If I can label this as x and y, then I know the area is x times y. That's one equation. Let's come back up here to fencing. That would go all the way around it, and so that would relate to perimeter, except I'm not going to fence in the river. So I would have 2x plus y is 3,000. So those are my two equations, and I want to take one equation and substitute it back into this one, into the other one that's going to ask me to either minimize or maximize. So here I think it's easiest to solve for y. So I'm going to substitute y. I'm going to put in place of y 3,000 minus 2x, and then multiply that out. Right, so that is the equation I need to maximize. So I'm going to take the derivative, I'm going to set it equal to 0, and I'm going to solve for x. And it says what are the dimensions? What are the dimensions and what is this area? So I not only have to get x, I have to also come back here and get y. So y is going to be 3,000 minus 2 times 750, which is 1,500. So my dimensions are 750 by 1,500, and my area would be those two quantities multiplied together would be 1,125,000 square yards. This is similar to the last exercise, the same rancher that has the same 3,000 yards of fencing, but this time he's enclosed another corral. So we have 3x plus 1y is 3,000 for that 3,000 yards of fencing. The area is still x times y because x times y would give you the area of the amount that he is enclosed. So we're going to solve for y. We're going to substitute into the other equation that we're asked to maximize. We're going to take the derivative and set it equal to 0. So I get x to be 500, and so that gives me a y value of 1,500. So those would be my dimensions, and then it asks for the area, which would be 1,500 times 500, which would be 750,000 square yards. Okay, so now instead of maximizing something, we're going to be asked to minimize a cost. Right, so we have a building and they've decided to enclose an area out here, so very similar to enclosing on the ranch. But this time they give us how much area we want to enclose. So the area is going to be 800 square feet, and they want to know how to build it. So they've got two sides to be constructed from pine boards and the other side to be constructed of steel. The pine board costs $6 a running foot and the steel costs $3 a running foot. Determine the dimensions that can be erected at a minimum cost. So let's see, we know that the area is 800. So let's see, what kind of variables are we going to give here? How about let's name the wood side x and the steel side y. So the area would be x times y. So 800 is x times y. So that's one equation. But how are we going to get a cost? Well, let's see, if the wood costs $6 a foot and x represents each foot of the wood, so 6 times x, and we have two sides, that would be the cost of the two sides, plus the steel would be 3 times y. And that would be my cost function. So let's see, 12x plus 3y equals the cost. Now, since I'm asked to minimize the cost, I need to come to this equation and solve for x or y and substitute it back into the cost variable. It doesn't really matter which one we solve for, so I'm going to solve for y by dividing both sides by x. Then I've come to this equation and substitute in 800 over x. That's going to be my cost function. And I'm going to take that x up to the numerator and make it a negative exponent, because in order to minimize this cost, I'm going to need to find the derivative. So let's see, that's going to be 12, equals to the derivative. I need to set that derivative equal to 0. So I'm going to go and put this back into the denominator. I'm going to solve for x. And now I'm going to cross multiply, and then I'm going to take the square root of 200, and I don't want to take the negative value because it would be a plus or minus, but since x is an area or a dimension, I just need to take the positive square root of 200. So let's see, as I go back up here, I'm going to have y is 800 divided by the square root of 200. Let's see if I can simplify that at all. The square root of 200 is 10 times the square root of 2. So that would go in there 80 times. So I have y is 80 over the square root of 2, and x is 10 square root of 2. You could leave your answer like this, but if you wanted to rationalize it, you would have to multiply by the square root of 2 over the square root of 2, and then reduce. So we have one side of the fence to be 40 times the square root of 2, and the other to be 10 square root of 2 in order to minimize the cost. Number 6 is a very classic calculus problem. Probably been in every calculus book ever written. Right? We're going to have a rectangular piece of cardboard, and we're going to cut away little squares, identical squares, on each corner. And then if you fold up those, you would make an open box. You ought to try it. It really does work. Right, so the cardboard was 15 inches long. Actually, I'm going to put it this way. This is 15 inches long by 8 inches wide. Find the dimensions of the box that will yield the maximum volume. Now keep in mind, this is going to be turned up. If you go and take a gift box or something and trying to put it together, you're going to get exactly this idea. All right, so let's see. How big, first of all, was these little bitty squares? What did I cut away here? Well, let's call that x and x. They're squares. So this part that's left right here is going to be the original 8 inches minus 2x, because you've got an x on this side and an x on this side. Then the dimensions here is going to be the original 15 inches minus the 2x. So let's talk about that volume. Remember, volume is length times width times height. So my length would be 15 minus 2x. The width, 8 minus 2x, but the height. So when you fold this up, you have a height of x. So let's multiply. If you multiply this out, what would you get? That would be my volume. Now, how are we supposed to maximize that? What other information did they give us? Well, they didn't give us any other information. We have one equation, one function that's already in terms of the same variable. So that's why we don't need the two equations. Let's go ahead and take the derivative. Let's see, that should be a 4x squared. So we have minus 92x plus 120. I'm going to set that equal to 0 and solve. I believe this factors. So I get x is 5/3 and x is 6. Now I have to know which one provides a minimum, but first of all, let's see, or a maximum volume. First of all, let's see if those answers are even possible. Right? Remember that my width was 8 minus 2x. So let's see, if x is this 6, I would have 8 minus 12 which would be a -4. That's not possible, right? If I let my width be, if x is 5/3, I would have a reasonable answer, or at least a positive answer. So the 5/3 is going to be my x value, and then I just need to go back and substitute in what is 15 minus 2x, which would be 15 minus 2 times 5/3, which is going to equal 35/3. Then I have 8 minus 2x, which is 8 minus 2 times 5/3, which is going to be 14/3. And then, of course, I have the 5/3. So those would be the dimensions of the box. All right, number 7 is the exact same setup, except that you have a 10 sheet that's 8 inches square. All right, so we have a square to begin with that's 8 inches by 8 inches. They're going to cut the same little identical square from the side. And so our volume is still length times width times height. But this time, our length and width is going to be exactly the same, that 8 minus 2x. And our height is the x, because when we fold that corner up, or fold that side up, that's going to be a height of x. So the same process, we would multiply that out. I'm going to take the derivative. I'm going to set that equal to 0. Solving for x, and now I'm going to go back and check to make sure that those can be the answers. So the length is 8 minus 2x, so 8 minus 2 times 4 would yield a length of 0, and I wouldn't have a box at all, so that is thrown out. So my length and the width is 8 minus 2 times 4/3, which would be 16/3. So my dimensions are 16/3 by 16/3 by 4/3. That would be the final answer. Okay, on problem number 9, we have the closed rectangular box, and it has a cross section with a square cross section, meaning this part down here, or really up here, is a square. And we have a volume of 128 cubic inches, and we want to construct it with the least amount of material. So I have a volume of 128. I also know that volume is length times width times height. So let's see what I have. I have length times width times height, so that's going to be x squared times y, and that's 128. So that's one bit of information that I have. But it asked about constructing the least material. That would be the outside, all the sides of the box. That's known as surface area. The surface area, if you take a box, and I would really like for you to get out a box and count how many sides, it has 6 sides. So we have a top and a bottom, and that's going to be the same. So the top and the bottom has an area of x squared, because this is x by x. All right, then we have this side right here, and it's mirrored on the other side of the box, and that area would be x times y. And then we have the front face, which is mirrored by the back one, and that's also x times y. And since we have 2 of each of those, I'm going to multiply all of that by 2. Now that's not the area, that's the surface area. And that's what we want to minimize. So let's see, let's kind of clean this up a little bit. So surface area, and see I have 2 of those and 2 of those, so that'd be 4xy. So now I need to substitute in a variable, substitute in x or y, so I can get this all in terms of x or y. So I'm going to come back to this equation, and I'm going to solve for y, and I'm going to substitute that in here. Okay, I'm going to set this, I'm going to rewrite this with negative exponents, so I can take the derivative, because I want to minimize it. I want to set that equal to 0. and I need to solve for x. How am I going to do that? Well, I think the easiest way would be to get rid of the denominator. So let's multiply everything by x squared. So I have this equation, and I need to set that equal to 0 and solve for x. So let's see, I'm going to have 4x cubed equals 512. X cubed is going to be 128. And then if I take the cube root of 128, the cube root of 128, that would be approximately 5.04. So you could leave it as the cube root of 128. You could simplify that, or the book says fine to use decimals. All right, so that's x. Now I have to come back up here and get y. So y is 128 over x squared, and that is going to be approximately 5.04. And y is going to yield the same answer, which seems kind of odd, but not really. In order to get the least amount of material when building a box, you really need to always build a cube. All right, let's look at this one. It says postal regulations specify when we send a parcel, it can't have a combined length and girth of no more than 108 inches. Length and girth. Find the dimensions of a rectangular package that has a square cross section, so again that x by x, and the largest volume. All right, and they give us a hint, I'm glad, because the length plus the girth is 4x plus h. All right, so it means when you wrap it around here, that's 4x plus h. And we have to have no more than 108 inches. So 4x plus h has to be less than or equal to 108 inches. And we want to maximize the volume. So to go back to volume is length times width times height. In this case, that'd be x times h, which is x squared times h. Since we want to maximize this, I'm going to change this to an equal sign, and I'm going to solve for h. And I'm going to substitute it in here. So I'm going to take the derivative, I set that equal to 0, set those equal to 0 and solve. So I'm going to get x is 0 and x is 18. So I think you can see that x being 0 won't give you a box. So we have an x is 18. So h is 108 minus 4 times 18, which is 36. And so our volume needs to be x squared times h. So that's 18 squared times 36, which would be 11,664 cubic inches. So what is the volume of such a package that big with the dimensions of 18 by 18 by 36?